Section 1 Introduction. We're going to talk about cognitive behavioral therapy, CBT, a well-established method in psychology. One of the key aspects of CBT is to recognize and reshape unhelpful thought patterns. There's been some success with low-intensity CBT interventions in self-help formats, but the lack of suitable practice material tailored to individual needs is a hurdle to widespread use. Modern language models, which can be guided to generate language in a specific way, such as matching a certain persona, style, or confidence level, could be a powerful tool for learning how to reframe thoughts. However, there's a significant obstacle: the lack of publicly available data. Most of the current research in natural language processing, NLP, for CBT is based on interactions between patients and mental health professionals, which aren't publicly accessible. There has been a public dataset released for reframing tweets marked with a stress-related hashtag, using known reframing techniques. But this dataset doesn't specifically address the categories of unhelpful thinking used in CBT, and it uses existing tweets rather than generating examples tailored to a specific situation. In our work, we're introducing a new dataset, which we're calling PatternReframe. It includes 10,000 examples of thoughts, each containing one of 10 classic types of unhelpful thought patterns. These thoughts are based on personas and are paired with suggestions for reframing that don't exhibit the unhelpful patterns. We're also introducing 2 tasks related to generating text: 1. Creating unhelpful thoughts, and 2. Reframing those thoughts, both based on a given persona and thought pattern. Additionally, we're defining a task to classify the unhelpful thought pattern, given a persona and a thought. We've trained and evaluated different approaches for these tasks, fine-tuning some and using a few-shot approach for others. We've found that these methods perform reasonably well on the tasks. Section Summary. Cognitive behavioral therapy, CBT, is a validated approach in psychology that focuses on identifying and reframing unhelpful ways of thinking. However, the lack of publicly available data and practice material tailored to individual circumstances has hindered its adoption. To address this, we introduce a dataset called PatternReframe, consisting of 10,000 examples of unhelpful thoughts and their reframing proposals, conditioned on personas and specific patterns. We also propose text-to-text generation and classification tasks on this dataset, and demonstrate that fine-tuned and few-shot approaches perform well in these tasks. Section 2 Related Work. In the section titled Related Work, we discuss 2 main areas: natural language processing, NLP, for mental health, and controllable text generation. In the realm of NLP for mental health, recent studies have utilized linguistic features and pre-existing language models to identify mental health conditions like anxiety, depression, schizophrenia, and post-traumatic stress disorder. Most of these studies have used social media posts to create datasets for their research, training, and evaluating various classification models. Some have even created datasets to identify unhelpful thoughts by annotating conversations between patients and therapists and fine-tuning pre-existing models for this purpose. However, these datasets are not publicly accessible. The work most similar to ours introduced a task of reframing, released a parallel corpus of reframed sentences, and used controllable text generation models to reframe social media content from Twitter identified as expressing stress. But this work did not condition the source social media material on personas or focus on the classical unhelpful thought patterns from cognitive behavioral therapy, CBT. Our work introduces this conditioning and extends the reframing task to identify and generate thoughts that match a given persona and unhelpful pattern. In the area of controllable text generation, approaches using pre-trained language models, PLMs, generally fall into 4 categories. 1. Prompt-based methods that either construct templates for PLMs to complete or fine-tune a task-specific layer to guide the generation. 2. Fine-tuning methods that either use labeled data prepended with controlled attributes or define a task-specific reward function using reinforcement learning. 3. Post-processing methods that train discriminator models to guide the generation towards a specific criterion during decoding. And 4. Pre-training methods that pre-train PLMs from the start with different control tokens prepended to the input. In our research, we experiment with both prompt-based and fine-tuning methods. In the section titled Identifying and Reframing Unhelpful Thoughts, we use the 10 categories of unhelpful thought patterns described in a popular CBT self-help book. These categories are listed in a table with examples provided for each. For reframing unhelpful thoughts, we follow 5 reframing strategies based on positive psychology. 1. Growth mindset. 2. Optimism. 3. Impermanence. 4. Neutralizing. And 5. Self-affirmation. We acknowledge that other reframing strategies exist, such as being mindful, or focusing on forgiveness and compassion. We provide the above 5 strategies as a starting point, but researchers are free to use other strategies. Section Summary. Previous research in natural language processing, NLP, for mental health has focused on using linguistic features and pre-trained language models to identify mental health conditions. However, these studies mainly rely on annotated social media posts and lack publicly available datasets. Our work builds upon this by introducing conditioning on personas and classical unhelpful thought patterns, extending the reframing task to generate thoughts matching a given persona and unhelpful pattern. In terms of controllable text generation, we experiment with prompt-based and fine-tuning methods. Additionally, we use 10 categories of unhelpful thought patterns and 5 reframing strategies based on positive psychology to guide our approach. Section 4.1 Data Collection. We'll now explain the 4-step process we use to gather our dataset. More details about this process and images of the interface can be found in the appendix. 4.1.1 Step 1. Creating negative thoughts. To create a wide range of negative thoughts that fit various contexts and situations, we use personas from the Persona Chat dataset. We provided these personas and one of 10 negative thought patterns to the crowdsourced workers. Their task was to write sentences that were in line with the given persona and displayed the specified negative thought pattern. 4.1.2 Step 2. Classifying negative thoughts. Negative thoughts can display multiple patterns, and these patterns can overlap. To capture this complexity and filter out low-quality data, we asked crowdsource workers to label the thoughts they had previously generated. They were given a thought and a list of negative patterns, and they had to identify all the patterns present in the thought. If the thought was irrelevant or didn't make sense, they could select a None option. We collected 5 labels for each thought and discarded any thoughts that were labeled as None by the majority of workers. 4.1.3 Step 3. Rewriting negative thoughts. For the third step, we asked the crowdsource workers to rewrite the negative thoughts in a more positive way. We provided them with the original thought, the persona, and the negative pattern that was used to create it. Their task was to rewrite the thought so that it still fit the context but didn't include the negative pattern. We also provided 5 strategies for rewriting the thoughts and asked the workers to indicate which strategy they used, if any. These strategies were only suggestions, and the workers were free to rewrite the thoughts in any suitable way. We collected 3 rewrites for each thought. Section Summary. The data collection process for the dataset involved 3 tasks. In the first task, crowdsource workers were given personas and unhelpful thought patterns to write sentences that matched the persona and exhibited the given pattern. In the second task, workers categorized the previously generated thoughts by selecting the patterns that appeared in each thought. Thoughts marked as None by the majority of annotators were discarded. In the third task, workers were asked to rewrite the thoughts containing unhelpful patterns in a more helpful way, using provided reframing strategies as suggestions. 3 rewrites were collected for each thought. Section 4.1.4 Task 4. Evaluating the rewrites of unhelpful thoughts. In Section 4.1.4, Task 4, we evaluate the quality of the rephrased unhelpful thoughts. Here's how we do it. We provide workers with a persona, an unhelpful thought pattern, a generated thought, and 3 rephrased versions of that thought. We then ask them to choose the rephrases that successfully eliminate the unhelpful pattern without contradicting the original thought. If a worker picks a valid rephrase, we ask them to identify which of the 5 suggested reframing strategies were used, if any. We gather 5 annotations for each set and only include the rephrases that a majority of annotators mark as valid. In Section 4.2, we discuss the quality of the data we collect. We use the Mephisto and Amazon Mechanical Turk platforms to gather our data. We use the second and fourth tasks to select a group of high-quality workers. These are workers whose generated work was validated by a majority of separate annotators in a separate task. We initially allow all workers to participate in the first and third tasks, which involve generating text. We add new workers to our selected group after each round if they have completed at least 5 text generation tasks with at least 80% of their generated text validated through the evaluation tasks. After 9 rounds, we ended up with 524 qualified workers. Once we had more than 500 qualified workers, we limited all tasks to this selected group. In our final dataset, we only included annotations provided by these selected workers. We also included onboarding tasks to ensure that the workers fully understood the concept of reframing thoughts. Only workers who passed these onboarding tasks were allowed to work on the actual tasks. We used Krippendorff's alpha to calculate the agreement between annotators. The scores were 0.355 for the second task and 0.454 for the fourth task. These scores represent the agreement on binary judgments made at the pattern level for the second task and at the reframe level for the fourth task. Section Summary. In Task 4, we evaluate the quality of the rewrites by providing workers with a persona, unhelpful thought pattern, generated thought, and 3 rewrites. They are asked to select valid rewrites that remove the unhelpful pattern without contradicting the source. We collect multiple annotations and include only the rewrites marked as valid by the majority of annotators. To ensure data quality, we use Mephisto and Amazon Mechanical Turk platforms, select high-quality workers through labeling tasks, and restrict evaluation tasks to the selected pool. We also calculate inter-annotator agreement using Krippendorff's alpha. Section 4.3.1 Dataset Statistics. In our study, we've compiled a dataset called PatternReframe, which includes 9,688 original thoughts and 26,507 rephrased versions of these thoughts. We've divided this dataset into 3 parts: training, validation, and testing. The training set includes 1,920 original thoughts and 5,249 rephrased thoughts. The validation set has 961 original thoughts and 2,623 rephrased thoughts. The testing set is the largest, with 6,807 original thoughts and 18,635 rephrased thoughts. Each original thought can have up to 3 rephrased versions. On average, after removing lower quality rephrases, each thought has about 2.74 rephrases. The average length of the original thoughts is 19.1 words, while the rephrased thoughts are slightly longer, averaging 23.9 words. We've also analyzed the types of unhelpful thought patterns in our dataset. Our analysis shows that some patterns overlap significantly. For example, the patterns of discounting the positive and mental filtering often appear together, as do fortune-telling and catastrophizing and personalization, with labeling and mislabeling. The pattern all-or-nothing thinking is hard to distinguish and overlaps with many other categories. The patterns mind reading and should statement show the least overlap with other patterns. We've also looked at the strategies used to rephrase the unhelpful thoughts in our dataset. Most rephrased thoughts use one of 5 strategies, with very few labeled as none. The strategies, growth mindset and optimism, are the most commonly used, followed by neutralizing and self-affirmation. The strategy, optimism, is particularly common for patterns that focus on the negative aspects of a situation, such as discounting the positive and mental filtering. Finally, we've used our PatternReframe dataset to train and evaluate different models. These models are designed to generate, identify, and rephrase unhelpful thoughts, all while taking into account a given persona. Section Summary. The dataset used in this study, called PatternReframe, consists of 9,688 thoughts and 26,507 reframed versions of thoughts. The dataset was split into training, validation, and test sets, with an average of 2.74 reframed versions per thought. The analysis of unhelpful thought patterns revealed high overlap among related patterns, while the analysis of reframing strategies showed that growth mindset and optimism were the most commonly used strategies. Different models were trained and evaluated on the tasks of generating, identifying, and reframing unhelpful thoughts. Section 5.1.1 Task and Data. In this section, we're discussing the task and data involved in our study. Our aim is to create a thought that aligns with a given persona and exhibits a specific unhelpful thought pattern. We approach this task as a typical condition generation problem, and during training, we aim to optimize the maximum likelihood loss. We use the training, validation, and testing splits as described in the following section. We assess our methods based on fine-tuning and few-shot learning. We fine-tune 3 models: BART large, T5 large, and R2C2-3B, which is a BART-based language model specialized for dialogues. For the input, we combine the persona and the unhelpful thought pattern texts using a special delimiter token. We also generate responses with GPT 3.5, a cutting-edge language model trained to follow human instructions, as a one-shot method. However, we only generated thoughts for 100 random inputs in the PatternReframe test set due to limited access to the GPT 3.5 API. In terms of automatic evaluation, we use metrics such as Blue, Rouge, and BERT score to measure the semantic similarity between the generated thought and the human reference. We also use distinct -1 and distinct 2 metrics to measure the diversity of the generations. These metrics calculate the ratio between the number of unique n-grams and the total number of n-grams in a generation. The results show that all models perform similarly in terms of Blue, BERT score, and Rouge. However, GPT 3.5 generates the most lexically diverse rewrites with the best distinct end scores. We also conduct a human evaluation, as automatic metrics often don't fully capture human preferences in text generation tasks. We collect human ratings of 100 random thoughts from the test set. We evaluate the generated rewrites based on 3 dimensions: fluency, meaning preservation, and quality. Fluency assesses the readability of the generation, meaning preservation checks if the rewrite aligns with the given persona and thought, and quality evaluates if the generated thought exhibits the given unhelpful thought pattern. We collect 9 annotations for each system output and use majority voting to determine the final annotation. The results show that GPT 3.5 outperforms all other approaches in terms of fluency and quality. However, GPT 3.5 has the lowest score for meaning preservation. The other models struggle more with including the unhelpful pattern, resulting in lower thought quality scores. Section summary. The task in this section is to generate a thought that aligns with a given persona and exhibits a specific unhelpful thought pattern. The models are evaluated using automatic metrics such as Blue, Rouge, and BERT score, as well as human evaluation in terms of fluency, meaning preservation, and thought quality. GPT 3.5 performs well in terms of fluency and quality, but struggles with meaning preservation, while the other models have difficulty including the unhelpful pattern. Section 5.2.1 Task and Data. In this section, we're discussing a task where we have to categorize a persona and a thought into one of 10 unhelpful thought patterns, or none, if the thought doesn't fit any of the patterns or doesn't match the persona. We're treating this as a classification problem with 11 categories. We're using the same training, validation, and test splits as before. Our dataset only includes positive examples, meaning thoughts that match a specific pattern and persona. For each positive example, we create a negative example by randomly selecting a thought from our dataset that either belongs to the same pattern but a different persona, a dialogue text from persona chat that belongs to the same persona but doesn't contain an unhelpful pattern, or a dialogue text from persona chat that belongs to a different persona and also doesn't contain an unhelpful pattern. These negative examples include neutral texts and thoughts that don't match the personas. We label these examples as none. After adding these examples, we have 3,834 training, 1,915 validation, and 13,572 test instances. We fine-tune Roberta using a soft label distribution, which we obtain by asking multiple annotators to identify the patterns in a thought and then normalizing the votes across the patterns. We use a soft label distribution instead of a single label because of the high overlap between patterns. We also perform an 11-way, one-shot classification using GPT 3.5. We create the input prompt using one example from each category and classify 100 random inputs in the test set. We evaluate our methods using confusion matrices for Roberta and GPT 3.5 on the augmented version of the PatternReframe test set. Since some unhelpful thinking patterns are closely related, we group the patterns using the k-means algorithm. Roberta performs well on all categories, except for the mislabeling category, which overlaps significantly with the polarized thinking category. The none category performs the best, indicating that the classifier can differentiate neutral texts that don't contain an unhelpful pattern or texts that don't align with the persona. One-shot classification using GPT 3.5 doesn't perform as well as fine-tuned Roberta. GPT 3.5 struggles to distinguish texts with and without unhelpful patterns and scores low for none. We also noticed that 40% of the classification predictions for GPT 3.5 changed after we reordered the sequence of examples in the prompt, suggesting that few-shot classification isn't as reliable for this task, even though it still performs significantly better than random chance. Section summary. The task in this section is to classify thoughts into one of 10 unhelpful thought patterns or none, based on a given persona. The dataset contains positive examples aligned with specific patterns and personas, and negative examples are constructed by randomly choosing thoughts or dialogues that do not contain unhelpful patterns or are misaligned with the persona. The classification is performed using Roberta and GPT 3.5, with Roberta performing well on most categories except for mislabeling, and GPT 3.5 struggling to distinguish texts with and without unhelpful patterns. Section 5.3.1 Task and Methods. In Section 5.3.1, we discuss the task and methods used. The objective is to rephrase a thought, which is based on a specific persona and an unhelpful thought pattern, in a way that aligns with the persona and the context, but without the unhelpful pattern. This reframing task is similar to the generation task, but the unhelpful thought is now part of the input, not the target. We use the same training, validation, and testing splits for this task. We also apply the same methods as previously described. For fine-tuning methods, we combine the persona, the pattern, and the thought texts with a unique token. For few-shot methods, we create a prompt similar to the one used for the generation task, but with the reframed statements. In section 5.3.2, we present the automatic evaluation results. We use metrics such as blue, rouge, BERT score, and distinct N. Since each unhelpful thought can have up to 3 reframed versions, we take the highest of the 3 scores and report the average of these highest scores. The R2C2 model performs the best in terms of blue and BERT score. GPT 3.5 outperforms the other models and human references in terms of distinct -1 and distinct 2 scores, indicating that the generated thoughts are diverse in terms of vocabulary. In section 5.3.3, we discuss the human evaluation results. We evaluated 100 reframed thoughts generated by different models based on the persona, the pattern type, and the unhelpful thought from our test set. We evaluated the reframed thoughts for fluency, meaning preservation, and quality. We asked the evaluators if the reframed thought removes the unhelpful pattern while being consistent with the original thought. All models perform close to human reference in terms of fluency and meaning preservation. In fact, all the outputs of R2C2 and GPT 3.5 are fluent and preserve meaning. For reframing quality, all models perform over 70%, but GPT 3.5 performs the best. GPT 3.5 feat's superiority is even more marked when using the more stringent threshold of 7 out of 9 evaluators rating positively. Overall, the evaluation suggests that using modern models to produce reframing is a feasible approach, even with a small amount of data for fine-tuning. In particular, GPT 3.5 performs remarkably well and very close to crowdsourced worker performance, only based on prompting. Section summary. The goal of the reframing task is to modify a thought that exhibits an unhelpful pattern in a way that aligns with a given persona and context, but without containing the pattern. The evaluation results show that GPT 3.5 performs exceptionally well in terms of fluency, meaning preservation, and removing the unhelpful pattern, indicating that using modern models for reframing is a feasible approach even with limited training data.